Hello, hello, AP Calculus AB. Here we are for our notes for the rest of 1.2 and start on 1.3. So I am filming this on Sunday, so I don't actually know how far we'll get in the notes this Wednesday, but I'm just guessing we'll get to here. If I'm wrong and if we got past the absolute value functions on Wednesday, then you can just go ahead and skip ahead to the appropriate place in the video. All right, so we're going to start talking about absolute value, and it comes right after our piecewise notes because absolute value is actually a piecewise function. You graph it in pieces. There's different rules for each piece of the absolute value. All right, so when we deal with absolute value, you've got two options here for x. What could x be? Well, x could just be itself, right? If this were the absolute value of 3, then x could be 3. But if this were, the absolute value of -3, you would also be getting the same answer out of 3, right? Because absolute value is the distance a number is away from 0 on the number line. So I can answer this other piece of -x. So, if x is, if x just pops out and is itself, that means x was a positive number. So we write that as greater than 0. But what this means, this doesn't mean a negative number, this means the opposite of. So if the original x right here was negative number, what's going to pop out is the opposite of that negative number, which indeed is then also a positive, and that's for values less than 0. Okay, so that's how we write that. So this just means positive, the absolute value pops out, absolute value of 3 is 3, and this is just for negative values. Absolute value of -3 is -3, which makes it positive 3. All right, so we've left out 0 here, so we have to put 0 into our rule, and we traditionally put it with the positives. You don't have to. You could put it at the bottom, but traditionally you just include that 0 right here. Okay, and so you just get this V shape. It's linear on both sides here, and these are just, every input results in a positive output because, again, the big idea is it's the distance a number is away from 0. So positive inputs, positive outputs. Negative inputs, they get negated, and positive outputs. All right, and so just to kind of generally speaking, whatever's in the absolute value, if that blob is positive, the blob comes out as itself for positive values here, and the blob comes out to its opposite for negative values. All right, I know blob's kind of a weird word, but we use it, quite a bit here. Okay, so let's just do one of these, and you'll do one of these on a quiz, and you'll have this whole process, and I'll be checking the process. So a big part of calculus is showing your process, and we lead you through it in the notes and the worksheet so you know what to expect. All right, so write g of x equals x minus 2, absolute value of, as a piecewise function. And so for this example, the expression x minus 2 is, what we're referring to as the blob. So you just go through this process and get the two pieces. So it will be the blob itself for blob values greater than or equal to 0. It will be the opposite of the blob for blob values less than 0. Okay, so that's the process, and then we show the next step where we just kind of make it a little cleaner. So just, that's going to be for x values greater than or equal to 2. So just make sure when you put the blob here, you don't put x greater than or equal to 0. This is the blob value when you're defining your domain. Okay, and so this is -x plus 2, and this is for blob values less than 2. So each piece is linear, and then it has these different rules, right? Those are called domain restrictions. So what can x be, in this situation, and what can x be in this situation? In this situation, x has to be greater than or equal to 2. In this situation, x has to be less than 2. So 2 is a pretty big number. This is where the rules change. So we're going to put 2 right here. And if you think about 2, if you plugged 2 into either one of these equations, you'd get 0. So we've got this point 2, 0. And so we've got a point, and let's just use our slope. This has a slope of 1, so we're going to go up 1 over 1, up 1 over 1, right? Okay, so we'll just give another point here. So there's your side of the absolute value. And then same thing here. This is going to have that kind of critical number where the rules change. But this slope is negative. So instead of going down 1 over 1, I'm going to go the other way because this definition is numbers to the left of that critical number. So instead, I'm going to go up one and, I'm going to go up one and left one. And there's this other side here. So, you got this point 4, 2, and you've got this point 0, 2. Makes sense for this y-intercept right here, so it all kind of comes together. So that's one way to think about it with the process. Another way to think about it is transformations from the parent graph. We know that this simply went right to, if you know your parent graph, that V shape, and you know that when something occurs within the grouping symbol, it's horizontal and it goes opposite of that sign. Okay, so, and then if you were talking about minimum values, you get a minimum value of 0 that occurs when x is 2. So that's your minimum value and occurs at x equal to 2. This is kind of the when. And this is what it is. When does it happen and what the actual value is. All right, so let's see what's on my next page. Okay, so we have another one, and in this case, the blob is x plus 1. It's what is in that absolute value. We don't really care about this -4. The blob is here because rules will change for it, whether it's positive or negative. Okay, so let's go through the process. So it is just going to be itself, and that's for blob greater than or equal to 0, and it's going to be the opposite. I'll just go ahead and do like that. For blob negative. Okay, so be careful that you don't switch the sign of this -4. That -4 is not affected by, the distance a number is away from 0 because it's not encompassed in those symbols. All right, so let's clean it up. So this is x minus 3 for x greater than or equal to 1, and this is negative x minus 5 for x less than or equal to -1. Oh, I didn't really write my negative there. Okay, so again, -1's a pretty big place where the rules are going to change. So let's see what happens at -1. If you were to put -1, into here, you're going to get -1 minus 3 is -4. If you put it in here, you're going to get -1 of -1, which is positive 1 minus 5, which is also -4. So this is, again, should be, you should be thinking that this is consistent with all of the transformation talk you've done in other classes. Okay, again, each piece is linear with domain restrictions. Okay, this is, again, you can kind of get that vertex, or you can get that vertex right here where you see -1 minus 4. It's another way to think about it. You may be thinking, why would we even do this when I can just think about -1, -4? I get you, but it's just nice to see things in two different ways and then just to notice all the connections. All right, and so, this is linear, so this slope is 1, 1. We do a lot of talk about slope in calculus, which is why we talk about the slope here. This slope is, 1 over 1, and this one is -1 over 1. So again, we can just go 1, 1, 1, 1, get some points here. There's this V shape. And then this one, instead of going down 1 and over 1, I'm going to go to the left side because that's, this rule is for the left of -1. So instead, I'm going to go up 1, left 1. Okay. And there you go. Always nice to label a couple of points. 1, -2, we'll put right there, 1, -2. And let's put -2. Well, let's put -3, -2. Okay, 1, 2, 3, 1, 2. Okay, so there's that. Describe the transformations. This would have gone right. Let's go. So just instead of left 1 and down 4. The minimum value here is -4 when x is -1. Okay, so check that box for absolute values. Let's go to composite functions. Okay, composition of functions. You've seen this before. This is when the output of one function becomes the input of the next. So we've got f and g here, and there's two ways you'll see this written. Sometimes you'll see f of g of x, like the kind of parentheses. You can see the input, g of x is the input of f, and so you get the double parenthesis kind of look there, or you can use this symbol here. Now this is an open dot. It almost looks like a degree symbol, but that's not multiplication, nor is multiplication composition. So this open dot means composition. All right, and you're just gonna, this one you're gonna plug G into F, and this one you're gonna plug F into G. Okay. So sketch the graphs of the compositions. Based on your graphs, predict the domain and range for each composition. All right. So let's do f of g of x. So I'm going to take f and I'm going to plug g into it. So here goes g into f right here. All right. And so this is a square of a, sorry, I was covering it, a square of a square root. So this is just x plus 2 minus 3. So this is simply x minus 1, okay? And so we've got here, there's that. And it's super easy. You just get one more point on there. And so this is the graph there of, that one was f of g of x. Okay, so we've got this nice line. Now it looks like that our domain, I'm going to do this in interval notation. It looks like our domain is all real numbers. That's what it would be for a line, and our range is all real numbers. However, that would be correct if this was the original problem, right? This is the composition of the two, but it's not the original problem. You have to base your domain on the original problem. Okay, so let's look at this. There's no domain restrictions here. This is just a parabola shifted down 3, so there's no x values that are going to cause me any trouble. No bad guys here. But right here I've got some, I don't want an imaginary. I don't want any imaginary numbers. So I've got some domain problems here. This is a square root graph, so I need to look at the fact that with g of x being root x plus 2, x plus 2 needs to be positive or 0, okay? So we don't get imaginary numbers. So x has to be greater than or equal to negative 2. So I have to use this restriction from the original problem and respect it for the composition. So this domain is actually going to be negative 2 to infinity, and I'm going to adjust my graph to start it at negative 2, and that's negative 2, negative 3 is going to be the start. And it's inclusive because it's okay to have 0 under there. Okay, so what does that do for me? That, well, you always get the range from, you know, the domain. So the domain is here, so that's going to impact my range also. Since the problem starts at negative 2, which is at negative 3, that range isn't going to go down any further. So this range is going to be adjusted, and you calculate that by, you know, seeing what happens with the domain. The domain's kind of in charge, and the range is, you just check out what's going on. All right, so make sure if you do something like that, you respect the original domain because it's going to affect the composition. All right, so now let's go this way. We're going to plug f into g. So let's go here. X squared minus 3 plus 2. So I'm just putting this x squared minus 3 plus 2 in there. So this is going to shake out to be x squared minus 1. Okay, that's going to shake out to be x squared minus 1. All right, so sorry, my computer is glitching a little bit, so we're getting a little pauses here, so sorry. Just keep on listening. It'll work itself out. All right, so now I've got this composition, so we're going to talk about graphing that. We're going to talk about the domain and range here. Okay, so, you know, let's come back to this one. So g of x was the input, right? G of x was the input, and this input had a restriction. So the input had this restriction of x greater than or equal to negative 2, okay? And so we had to respect that, right? And then we just kind of see what happened in terms of the composition, because, you know, once we were here, there were no restrictions. So this one's a little different. So f of x has no restrictions, okay? This is just all real. So I don't have to really worry about that. And so once it goes into G, we'll get the big picture, domain and range by assessing what happens. So here, we can't just get the domain and range by assessing what happens. We have to respect the input's domain restriction, which is g of x. Here, the input does not have a restriction, so this one we're just going to assess the domain and range from here. And we don't have to worry about anything from the beginning because there was no problem with this input. Okay, so how are we going to graph this? I think we did this. I'm going to do this back here on one of these problems, but we'll just talk about again. How are we going to graph this? A couple of things you could do. You could do some region testing if you like, to just kind of see what happens. You could set it equal to 0 and see what happens. You could use your conic sections. You could kind of think of this as y equals this, and you could square both sides and sort of play with it, and hopefully from your conics you can see that this is a minus. They're both squared, and this is minus. This is a hyperbola, okay? And they're they're centered at 0, 0 because nothing's being subtracted, and these are over 1. So they're going to be here and here. So you've got this top, you've got this hyperbola. But now notice I actually put the square in there. So I put the square in there. So if I were to go backwards and square root this would have been a plus or minus. So imagine you started here and you solved for y. There would be a plus and minus here. Well, in the original problem, there's no plus and minus. So I have to respect the original problem and just analyze the top part of this, okay? You don't get that bottom part of this hyperbola. So this is the top half of a hyperbola. See, this is 1, 0, and this is negative 1, 0, okay? And so the domain then is negative. You can just assess what's going on here. We go there. We're going to include that and go with the union, just like that. And then the range is 0 and up, up. All right. So if you were to use region testing, you would have basically set this to 0. You would have squared both sides. You would have gotten these critical numbers of plus or minus 1. You'd have put those here. Okay, and you would have, you're saying to yourself, I need x squared minus 1 to be positive. This is what we need for this situation. And so we would just test, say test 0 right here, and 0 squared minus 1 would be a negative, so that's no good. If I tested, say, 2, you'd get 4 minus 1, which is a positive, so that's, that's what we're looking for. And same thing here, if you were testing negative 2, you'd get 4 minus 1, which is 3, which is also positive. So you could also get your domain here and think about your graph kind of that way. I like the conic section piece better, but you could also realize that your graph is only going to graph to the right of 1 and to the left of negative 1 inclusive, and then kind of know the shape of square roots and how they have that curve to them. All right, let's verify algebraically that these are indeed these are indeed the domains, okay? And so I don't think we need to do that because I kind of did not follow the directions. I kind of did both in the same. So here it said just to graph it and see what you get, graph it, see what you get, and then here says, so let's do it algebraically. So I just did them both in one swoop. Well, if you graph this, you're going to see that. Here's the algebraic piece. If you graph this, you're going to see that on the TI. Here's the algebraic piece. Okay. All right. So this is basically C above. Up here was just supposed to be the graph. Okay. So sweet. All right. Let's see what's next. Ooh, we're in 1.3 now. Okay. 1.3 exponential functions. Let's see how far we can get here. I don't want to go too much longer. So exponential functions. Okay, so an exponential function basically has the variable in the exponential position. A we call our base. X we call an exponent. All right. So exponential functions, are always increasing or decreasing. Let's just kind of go here first. This is 0, 1. This is exponential growth. Okay, so that's an increasing graph, strictly increasing. We call it monotonic. Decay goes like this. going through 0, 1. These are very basic. They haven't been shifted at all. And so this is strictly decreasing. Okay, so they're also one-to-one functions. So I'm going to write strictly increasing or decreasing. Okay, so we're not going to have a base of 1 in an exponential function because 1, so any power would just be 1, so that's kind of silly. And we're going to have a positive base, okay? And this goes hand in hand with our logarithms and all of that later. We're going to have a positive base here. We're not going to be raising a negative base for exponential functions. In exponential functions, this a is going to be maybe your doubling factor or your tripling factor, so just having a negative number there just really doesn't make any sense. So if a is greater than 1, then it's growth. So if you're doubling or tripling, it's growth. If you're earning 5%, 1.05, so on and so forth. If a is in between 0 and 1, so some fraction, some positive fraction in between 0 and 1, then it's decay. So maybe it's 1/2 for half-life, maybe it's, 5% decay, which would be your 1 minus 0.05, which would be 0.95, which is in between 0 and 1. So that's your growth and decay. And these two properties, very similar properties of exponential growth. A is greater than 0, decay. A is, or B, and they're using B here, between 0 and 1. All right, so domain is always all reals for both. Okay, this is always going to be above the x-axis, so not including 0 and up. And this is, again, for the parent, not if it has shifted, so those are the same for both. Y-intercept is 0, 1 for both. Okay, so just think about if you ever put anything to the 0 power is 1, anything to the 0 power is 1. So when I plug 0 in here, there's 1. Graph is above. Graph is above. Okay, this is increasing at an increasing rate. Okay, it's increasing. Look at how, if you're walking uphill, right? So that's increasing. And the slopes are getting steeper. Okay, the slopes are getting steeper, so it's increasing at an increasing rate. So that's just like how you're walking, uphill, downhill. This is looking at the slopes. This is decreasing here, and this one is a little bit strange because you're walking downhill, so it's decreasing. But this is also, what should we say? And increasing. This is also decreasing at an increasing rate. Okay, super weird to think about because that looks steeper, right? But remember, these are negative slopes. So a -2, say here, is actually smaller than, this, say, -1/2. The easiest way to figure out this piece throughout all of calculus is to look at concavity. Concave up, those are at an increasing rate. So that's always easier for me to think about because my brain just wants to say that this would be decreasing at a decreasing rate because this looks like it's slowing down, but think about those are negative slopes. So the concavity, that's concave up, so that'll be an increasing rate. That's concave up, that'll be an increasing rate. More to come on that later. Okay, in behavior, as x goes to the far left, what is happening here? So as x goes to the far left, that is telling you to look far left. Okay. So as x is going far left, we are leveling out to 0. We are approaching 0, okay, which means that we have a horizontal asymptote on the left-hand side. All right, and then here, what's happening as x goes to the far right? What's the limiting value? This means kind of like the limiting value is x goes to infinity, positive infinity, negative infinity. This is also leveling out at 0, so that means we have a horizontal asymptote on the right-hand side. Okay, and then just some graphs here, discovery activity. So these are all going to have the same critical, y-intercept right there. But this one's just going to be, steeper, and this one is going to be in the middle, and this one's going to be, the less steep one. Okay, so if you were to go on your TI and graph these, you would see the most steep one here, next one here in the middle. And this is just rough sketch. And then this guy. I mean, it's very hard to distinguish between these. If I was sharing my screen on a Google Meet, I would pop onto Desmos, which I actually should show you if you want. Super quick. So 5 to the x, 2 to the x. Oops, let's do 3. And 2 to the x. Okay, so you're going to watch, you'll see the 5 go first. There you go. There you go. There's the 3 to the x. And there's the 2 to the x. So very, very similar here over on the towards the asymptote, but you can see the difference right there. Okay, and then on this other side, these are all, decays here because you've got this 5 to the negative x. So same type thing. The one that is involving that 5 right here. So you get that kind of, think of this, if you wanted to think of it as 1/5, or if you wanted to think of it as 5 and then negative x, that would be a horizontal reflection. So basically, it's going to look exactly like this, but it's going to be reflected over the y-axis. So this 5 is still going to be the most steep, if you will. So let's do that again. Okay. So this was my y equals to 1/2 to the x. This one, middle one here, is my y equals 1/3 to the x, and the most steep is my y 1/5 to the x. Or you could keep it at these negatives. So I don't know why this one said 1/2, and this one said 5 to the negative. That's a little weird, but they all mean the same thing because of that negative exponent. Means that this 5 is 1/5, and the non-negative exponent would become negative if I put 3 to the numerator, so on and so forth. Okay, biggest thing you just want to get out of this is to see the similarities, and then just the base. The bigger the base, the more kind of steep the graph. All right, what's next? So this is super easy. Let's do some transformations, and we'll probably call it quits right here at exponents. Okay, so just quick review. This is a vertical shift up C, okay? And so if C is positive, you go up, and if C is negative, you go down. So it's the C moves as itself. This one is a horizontal shift. And I'm just not going to say up here because it might be down if C were negative. So I'm just going to say a vertical shift of C. I don't want to use the word up. All right, because this is very general. I thought we were going to have both of them both. It's just plus, so that just means, if it's +4, go up 4. If it's -4, go down 4. This is a horizontal shift of negative C. Okay, so if that's positive, you go left. If that's negative, you go right. If that's negative, you go right. And that negative C is indicating that when you write it kind of in general. This is a vertical. Notice the top row, these are all verticals because the transformation is happening outside of the function, outside of the parentheses or outside of the function. So this is a vertical reflection over x. Okay, and whereas this one is a horizontal. Over y-axis. Okay, it's happening in the function, which is, why this is happening in the function, which is why this is a horizontal flip. This is a vertical stretch / compression by C. Okay, and so stretch is if it's a number greater than 1. Compression is if it's a fraction between 0 and 1. And this one is a horizontal stretch / compression by 1 over C. So if I would analyze whether it's a stretch or compression once you've reciprocated the C. And then the numbers that are greater than 1 are your stretches, and the numbers that are the fractionals between 0 and 1 are your compressions. But you want to make sure with the horizontal stretch compression, you analyze that after you reciprocate that value that is in the function right here in the parentheses. Okay, so let's describe the transformations, and then let's graph these things. Okay, so describe the transformation here. So you always want to do this last. State this last. You want to state them in order. Typically, we say let's do all the horizontals first and the verticals second, and always list the shifts last. And that's just universally how we kind of teach it. So this is a horizontal reflection over the y-axis, and this is a vertical shift up one. All right, so this is still, you know, if we'd want to go in and kind of think about our parent, which would look like this. Okay, but we want to reflect it over the y-axis, and we want to bump it up one. So this parent is going to change to here. Okay, and so think about if I put 0 in there, this whole thing will be 1. 1 plus 1 is 2, and then it's going to be this way. So this asymptote is going to shift too. The asymptote used to be at 0, but now it's going to be here at x equals 1. So be careful that you shift your asymptote accordingly to with the vertical shift. Okay, so the domain is still all real numbers. The range is now 1 is that kind of limiting value down here. It shifts as well with the shift there. The x-intercept, there's none. We're not going to cross the x-axis. The y-intercept is 0, 2. And we have an asymptote of x equal to 1 on the right-hand side. Right-hand side. All right, one more here, and I think we can cover all of that on Monday. Describe the transformations from e to the x, then sketch domain range, find the intercepts, and our asymptotes. Okay, so let's list this first. This is a vertical stretch by a factor of 2, and this is a vertical shift down. Okay, so we're going to take that key, you know, we're going to, stretching it, there's not a whole lot, you know, for us to look at there. You know, we could, these are just really, they have such similar shapes that, I mean, we'll do what we can do with the vertical stretch by 2, but, you know, it's really kind of hard to get it really precise because these graphs are so exponential on one side and so flat on the other. Okay, so let's take this key value. Let's kind of work with this key value on the parent of 0, 1. Okay, so first thing I'm going to do is I'm going to stretch it by a factor of 2. So vertical, that's going to take this to 0. That's going to take this to 0. Okay, so 0, 2. And then I want to apply that, you know, that's times 2 for the vertical stretch by 2. And then I want to downshift it by 4. So that's going to be, you know, minus 4 on the y value, because that's your vertical. That's going to be negative 2. So this is going to be our new key value. Oops. It's going to be our new key value. Okay. And so E is, you know, positive. So this is going to be growth. You know, you've got your second e first power, whoops, e to the first power. It's just your 2.718, right? Compare e to like pi. It's just a number like pi is. Okay, so it's going to be growth. And so we just want to talk about so we're going to be going this way, so we're going to talk about our asymptote. So your asymptote is just going to be right here, this negative. It's going to be shifted by this, you know, this negative 4 here. This is going to be your asymptote. So you're going to take that original parent function of 0. Okay, the parent function rate has x x equal to, this y equal to 0 right here. Did we draw a parent anywhere? Right here, this has got this y equal to 0, HA. This has this y equal to 0, HA. Okay, and this is left-hand side, and this is, right-hand side. Okay, so if we take that original, thinking about it, here, this is going to be growth. So I'm taking this y equal to 0 on the left-hand side. I'm going to stretch it by 2. Well, 0 times 2 is still 0, and then I'm going to downshift it 4. So the asymptote here is 1, 2, 3. It's here. Y equal -4, left-hand side. And that is enough to get this graph going. I'm just not too worried about the stretch here and being able to notice it on the graph. As long as you state it, it's good to go with me. So domain negative, infinity to infinity. Okay, range we are greater than but not including 4. Our x-intercept we'll get to in a second. Our y-intercept is 0, -2. And we've already said we have this asymptote. Oh my gosh, what is wrong with me? I'm so sorry, you guys. Y equals to -4 on left-hand side. This is y. Goodness gracious, this is y. This is y. Sorry, you guys are probably sitting there going, what? Okay, that's y. Did I do y over here? Yeah. Okay, so I only goofed it up in one place, right? Okay, I think that's good. So sorry about that. And so now let's get our x-intercepts. Okay, so our x-intercept is going to be where we let y equal to 0. So x-intercept, I'm going to set this equal to 0. We're going to move 4 over. We're going to divide by 2. And we're going to take the ln of both sides, right? We're going to use ln with a base of e because they knock each other out. All right, and so x is just equal to ln of 2. All right, so x-intercept is ln of 2, 0. All right, I think that's it. Oh my gosh, 37 minutes. Welcome to AB Calculus. Hopefully I didn't make any more goofy errors there, but I think we're good. All right, I'll look forward to seeing you guys when I get back. Have a great weekend, and I'll see you Monday. Bye.